Hello.
Hello guys, nice to see you. Good afternoon.
Good afternoon.
Good afternoon. Hi.
Hello.
Hi. Good afternoon. So, first I would like to mention that we will have our third midterm this week or on Saturday, so please plan accordingly. So it will cover materials up to thermodynamics and molecular physics, so what we consider this week. So these topics from this week will not be included. Means all topics from mechanics which were not included in first two midterms will be covered by midterm 3. Okay, there were some questions also with respect constants, if they are given in the text of the problem. So some specific constants which are not, like some, for instance, G is not going to be given, that is quite established constant. But if we have some, for instance, radius and mass of Earth, since it could be given in different sources with some deviations, that will be specified in the text of the problem. So this type of kind of constants will be given. Yeah, other from that, I don't think that we have anything new. Will be real on Kappa. You will have 45 minutes to solve the 6 problems assigned. There will be 1 hour window for you to log in, but please log in beforehand. Don't wait until the last minute, because it better to avoid possible technical issues. Yeah, so during our previous discussion, we made some introduction of the thermodynamics, and temperature is one of the key macroscopic parameter, also the ways how we can measure temperature. Also we finished our discussion with the comparison of thermal expansion when we have linear and volumetric thermal expansion. We were getting the relationship between linear and volumetric thermal expansion coefficients. So far, we were talking about thermal expansion of solids. We assume that with increase of temperature, volume increases. That's kind of thermal expansion states for. However, there are some materials which possess unique features in terms of thermal expansion, and one of the most important one for sure is water. For instance, anyone can give me some explanation why ice is on top of water, and it's not why water is sinking, is freezing from top, not from the bottom. Because if you think about thermal expansion, then this is a bit counterintuitive, this result. So conductivity or thermal conductivity. Sure, it possesses thermal conductivity, but imagine you have some reservoir of water and some cold air outside. Well, lower density, you mean lower density of ice? That's true, but that's already the product of phase transition. But why this phase transition actually happens on the top, not on the bottom? That's the question. It makes hard to freeze from the bottom. So you mean that there is some warm volume of water which provides some heat, internal energy, and that's why it takes time until it's frozen. It makes sense, sure, that's kind of true. However, keep in mind that if we consider normal thermal expansion, means when we decrease temperature, the volume should decrease. Volume decreases means density increases. If density increases, so according to gravity, it's all in the gravitational field, heavier, denser surface water, which is cooler, should sink down because it's heavier, so the lighter, warmer should go up. And this process, the kind of convective process, should result in colder water underneath and warmer water on top. And that process will continue until it cools down to some point when the temperature will reach 0 and it will freeze. And since colder water underneath, it could be like kind of intuitively brings us to a conclusion that water should have freeze from bottom to top, but not in the opposite direction. So ice have lower density than water. We already mentioned that's true, but the key reason why freezing starts not from bottom but from the top was previously comment that the density is actually not like this thermal expansion is not so trivial for water, and then density at certain temperature close to 0 is not higher, it's actually smaller. So let us switch to the slide and we will draw one plot. So if we consider density of water versus temperature, then what do we see? At higher temperatures, when we cool down the water, its density increases. So it's quite expected trivial behavior. We in decreased temperature, we like water volume shrinks, density increases. However, at some temperature, which is 4 degrees Celsius, this density reaches its maximum and then starts to decrease. And here is, we can put 0 degrees Celsius because that's we don't consider lower temperatures, so probably will be better to redraw this, because at lower temperatures it changes its phase, so it's not water anymore. We cannot consider it as what, like liquid. Here is raw. So because of this unique feature, that in the temperature range from 0 to 4 degrees Celsius, upon decrease of temperature, density decreases, means we have observed some thermal expansion. Water freezes from top, because if we consider, for instance, some range from 4 to, I don't know, 7 degrees Celsius, and we cool down from 7 to 4, then density increases. Cold water, as I mentioned before, will be heavier, will sink down to the bottom of this reservoir. However, it will continue only until the surface of water reaches 4 degrees Celsius. Then density starts to decrease upon further cooling, and colder water is not anymore heavier, it's lighter. So it stays on top and allows to stay there for longer, interact with cold air outside, and start to freeze because its temperature goes to 0. So we have conditions for phase transition from liquid to solid state. And once we form some thin layer of ice on top of water, there is some thermal conductivity of this ice, and water next to this ice on top of water reservoir still continues to cool down. It in the temperature range from 0 to 4 degrees Celsius lighter, so it doesn't go down, and this freezing continues, so it kind of freezes from top to bottom. And at some point the thickness of this ice becomes so large that with thermal conductivity already is quite poor because thickness is large, and there is some equilibrium thickness of ice which reached with given temperature outside, and there is some water remains not frozen underneath. Of course, if the volume, if this reservoir is very shallow, it will freeze completely, but for deeper reservoirs, water underneath remains liquid, and that is the key requirement for life in this water. Because imagine if some lake freezes completely, then all fish in this lake would be dead. And that is true not only for fish nowadays, but that would be also true for the life evolution on our planet. That would have a great impact on life. It would be suppressed from further development and some microorganisms. And that played actually a key role in the evolution of life on our planet. And this feature of water should be mentioned, I think, and kind of should remember why it actually freezes from the top, not other way around. Okay, so we considered shortly some features of solid expansions and also unique features of water thermal expansion. Now we need to make next step and consider behavior of gases. In particular, we will deal with ideal gas. But before that, I would like to remind you this equation, which we considered previously. This equation allows us to calculate the thermal expansion, like change in volume, over some solid or water, for instance, where we have beta thermal, like volumetric thermal expansion, times initial volume times change in temperature. So means if we know this coefficient for some material which we are dealing with, then we can measure initial volume because it will be defined by the amount of material we take, solid and liquid. They have possessed some volume, depends on amount of material we take. Then we know temperature range where it changes, and we can calculate change of the volume because of thermal expansion. However, it doesn't apply to gases. So the thing is that interatomic forces in gases are so extremely weak that under some conditions, when we have quite low pressure, we can neglect with them at all and consider that we don't have any interaction. So gas occupies all volume which is provided by the container. So we cannot specify some initial volume for gas because no matter what, it will fill all container which is provided. So we cannot apply this equation for gases. In order to be able to deal with them, we need some to find some relationships between most important macroscopic parameters, which is pressure, volume, and temperature. So obviously they will be interconnected between each other. And our analysis we will carry out on some model system, which is ideal gas. So what is ideal gas? There is some definition for ideal gas. And for ideal gas, we assume that atoms of this gas, they interact with each other only in the moment of collisions. And there are no other interactions or they are negligibly small. Also, we consider atoms of ideal gas as mathematical points, so we do not take into account any internal structure of atoms or their size. These are mathematical points which are flying randomly in the container volume and interact with each other only in the moment of collision. It is convenient to express the amount of gas in some volume in terms of moles. So N stands for moles of matter, and 1 mole of any substance contains Avogadro's number of particles, like atoms or molecules. So Avogadro constant or number is equal to 6, 0.22, 10 to 23. So we have 6, 10 to 23 atoms in 1 mole of any substance and also in 1 mole of ideal gas. So how we calculate this moles? That is equal to mass of substance divided by its molar mass, which is measured by like in grams per mole, and is given is determined by the atomic mass of the chemical element which forms the, in our case, this gas. So with this in mind, we need to consider 3 most important possible processes in ideal gas. And let me change another slide. So we have, for instance, some cylinder with a mobile piston, and we have here volume filled with ideal gas. So we can consider three important processes. First of all, because since we deal with three parameters, pressure, volume, and temperature, we will consider three processes when each of these parameters remain constant. So first one is isothermal, when temperature is constant. So for this case, we can write that pressure is reversely proportional to volume. In other words, we can write that pressure times volume remains constant. No matter how the conditions will change, if temperature of ideal gas remains constant, then the product of pressure and volume also remains constant. Means if, for instance, we go from one state to another, so one state is described by a set of parameters P1 and V1, so temperature is constant. Then when it, because of this isothermal process, goes to another state, which is given by other values of, described by other values of pressure and volume, which is P2 and V2. So their product will remain constant, and that is very neat to know this, because you can apply this knowledge to determine some unknown parameter. So by the way, all this discussion about three processes here, they were obtained experimentally, so they're not derived from anything. These are empirical experimental results and observations. So another, like second process which we will consider is a process with constant pressure, so-called isobaric process. Isobaric process. So pressure is constant, and in this case we can write that volume is proportional to temperature. In other words, volume divided by temperature is constant. And also, if we consider two states of ideal gas, so when we go from first state to another via some isobaric process, when pressure remains constant, we can write that V1 divided by T1 is equal to V2 divided by T2. So one more process is remaining, and that is isochoric process, process with constant volume. We have isochoric process. Here we have volume as constant parameter, and in this case, pressure is proportional to temperature. So similar to the isobaric process, just instead of volume, we operate now with pressure. We have pressure over temperature is constant, and P1 over T1 is equal to P2 over T2. So taking this into account based on empirical observations of some experimental results, we can summarize all these three like features obtained for three different processes: isothermal, isobaric, and isochoric. And as a summary of this information, we can right now the equation of the state of an ideal gas, which is very important equation. You need to remember it, and you definitely will use it quite often. So the equation of the state of an ideal gas will be given in the following form. So this is the first form. We will consider about the second form a bit later. So we have pressure times volume is equal to N times R times T. So here we can write expression for this N, for number of moles, will be mass divided by molar mass times R times T. So here we know all parameters besides this R. So R is universal gas constant. So how do we get it? So if we consider pressure like approaching to zero, ideally, like very low pressure. So to be sure that we are in the range of applicability of these rules for ideal gas in under real conditions, then the ratio of P times V divided by N T will give us the value for this universal gas constant R. So if we operate with pressure in pascals, which is equal to 1 Newton per square meter, the value for this universal gas constant will be 8.314 joule mole times Kelvin. So another thing which you should consider is the physical meaning of this universal gas constant. So its physical meaning is the work done by 1 mole of ideal gas by expanding under heating by 1 Kelvin at constant pressure. So work done by 1 mole of ideal gas while it's expanding under heating by 1 Kelvin at constant pressure. So that is the definition of the physical meaning of this universal gas constant. Another important parameter and quite widely used, which is applicable for ideal gas, is the volume which a single mole of ideal gas occupies under so-called normal conditions. So if we assume that we have 1 mole of ideal gas, N is equal to unity, then V naught, like some special volume, will be equal to R, universal gas constant, times temperature divided by pressure. So here we need to specify that it's not just some random conditions, but very clear, clearly defined conditions. So first, temperature is equal to 0 degrees Celsius and pressure is equal to 1 atmosphere. By the way, what is 1 atmosphere in terms of Pascal? Do you remember?
Approximately 10 in power 5.
Okay, fair enough. 10 in power 5 Pascal. Also, keep in mind that, so we usually use Pascal in the course of general physics, but you may easily see some other units, specifically in industry, also in some vacuum deposition systems. Usually they are measured in, like pressure is measured in millibar. So 1 bar stands for 1 atmosphere. So 1 millibar is 10 to minus 3 bar, 1,000 less than 1 bar, which is something around roughly 100 Pascal. But we operate with, for all these calculations, which we need to do within this course with Pascal. So under these specific conditions, the volume V naught, which 1 mole of ideal gas will occupy, is 22.4 liters. So that could be also useful parameter. It is not constant, obviously, because if we change these conditions, temperature and pressure will be different volume. But since these are some common conditions and considered as standard conditions, we can also define it as some parameter which describes behavior of ideal gas. Another thing, like main conclusion from this the equation of the state of an ideal gas, that if volume and temperature, for instance, stay constant, then pressure also should remain constant. So that's some example with a bottle of champagne. So it's kind of considered that if you shake it, what is V naught? I mean, V naught is the volume of 1 mole of ideal gas under standard conditions given here. And I mean, it's given in liters, but you are asking in, as I understand, in cubic meter. Okay, but then what we have 1,000 liter in cubic meter, so you can consider it as 22.4 times you divide it by 1,000, get the percent of the volume occupied by 22.4 liters in 1 cubic meter. So you can convert these units easily. So if we consider a bottle of champagne, then and you shake it. So assume that you don't have too hot hands and you don't shake for too long, just shake it for a bit. You actually don't change neither volume, because volume is fixed, bottle is closed. You don't change also temperature, maybe a little bit, just tiny bit, because of this shaking, you may increase it a little bit, but that's almost negligible change in temperature. And this effect of kind of higher pressure, which you gain after shaking this champagne bottle, it doesn't come from increasing temperature, increasing pressure inside the bottle, actually. It just comes from the fact that by shaking, you create more bubbles inside the bottle. And that automatically increases the area, active area, from which gas can expand when you open the bottle and reduce pressure. if you create more of these bubbles, they expand from all directions, and that causes a very aggressive expel, like ejection of liquid from the bottom. So actually, you don't increase any pressure because you keep volume and temperature constant. You just increase active area of these bubbles in the bottom. So one more thing which we need to consider, that this equation for the state of ideal gas can be also presented in a bit different form, which may be useful for certain cases. So we can write it in terms of total number of atoms which are comprised in this volume and form this ideal gas. So we can write that pressure times volume. So we know it's equal to n number of moles times universal gas constant times temperature. Then we can express n as a ratio between capital N, which stands for total number of atoms, times RT divided by Avogadro's number. So number of moles can be given as the ratio of total numbers of atoms divided by Avogadro's number. So now we can write it as follows. It will be total number of atoms times mu constant Kb times temperature. So this mu constant Kb is Boltzmann constant, and it is equal to universal gas constant divided by Avogadro's number, and it is equal to 138 10 to minus 23 joule per Kelvin. So in this case, you can express the equation of the state of ideal gas in terms of, yes, capital N is the total number of atoms which form the ideal gas and are comprised in the volume V. So you can, yeah, you're welcome. And you can now express it not in terms of moles, but in terms of total number of atoms, which can be definitely useful for some specific case. So summarizing now our discussion. So first we considered some unique features of water in terms of thermal expansion, that it allows to remain, the bottom part of the water reservoir remain a liquid, and it freezes on the top of the surface because starting from 4 degrees Celsius and further cooling to 0 degrees Celsius, it actually thermally expands, not shrinks as would be expected. So that behavior is quite unique. Then we started to deal with ideal gas, if introduction, like introduce the features of ideal gas, meaning that we have some atoms which are considered as mathematical points, and they do not interact with each other besides moment of collision. For such an ideal gas, based on experimental results, we considered 3 important processes: isothermal with constant temperature, isobaric constant pressure, and isochoric constant volume. Explained how was found based on experimental results the relationship between other 2 parameters which still can change for each of these processes, and as a summary of all this information, we end up with an equation for the state of the ideal gas, introduce new constant, which is R, universal gas constant, define its physical meaning as work done by 1 mole of ideal gas while expanding under heating by 1 Kelvin at constant pressure, and also considered another form of this equation for the state of ideal gas, which is given in terms, not in terms of mole or number of moles, but in terms of total number of atoms that resulted in the introduction of another constant, which is Boltzmann constant. So you definitely, as a take-home message, need to remember these equations for the state of the ideal gas, and also remember and understand where these constants R and KB come from and what they are equal, because that is quite commonly used constants and quite commonly used equation for the state of the ideal gas. So I believe that it should be quite clear to this discussion. If you have any questions, you're welcome.
Can I ask?
Yes, sure.
Can you show one more time where we wrote like isochoric, isobaric, this, how to say it's formulas?
Yes, sure.
Okay. 1 minute, please.
Yeah, no problems. Yeah, so just a reminder, our discussions are available online. So if you need to look it through again, so you can check it anytime.
Yes, thank you.
You're welcome, no problems. Yeah, we have one more question.
Yes, I wanted to ask that in some resources, 1 ATM is equal to 101 kilopascals, but should we use it as 10 in power of 5 or as 101?
Or I think that, well, the correct number, more accurate number is 101 kilopascal. So that the value which you need to use in solving problems. But again, I believe that pressure will be explicitly mentioned in the problem, so you don't need to guess.
Okay, thank you.
But yeah, you need to use the most accurate value for parameters which are available. Yeah, you're welcome. Okay, then thank you for attention. We will continue discussing molecular thermodynamics. So we meet next time on Friday. Then have a good day, take care, and see you on Friday. Bye-bye.
Have a great day.
Thank you.
Thank you. Goodbye.
Thank you,
Bye.
goodbye. Thank you, goodbye.